Hi there, my name is Aaron Lanchman. I'm a professor of electrical and computer engineering at Georgia Tech. In the last lecture, we looked at a very strange circuit that could create a deadband-style nonlinearity by using just an op-amp, a couple of resistors, but interestingly, no diodes. Now in this schematic, I've used this R load to represent an input impedance of an inverting mixing stage that follows a set of these deadband circuits. And what Don would do is he would add and subtract the results of a bunch of these circuits with different weights, and he would pick various resistor values to achieve different deadband ranges and different slopes. And by adding these up, he could create these really complicated nonlinearities. And what he would do is he would do something like take a sine wave and place it through this nonlinearity. And if the amplitude of this was fairly small, you would get a sine wave out because you would be operating in this linear part. But as you started to increase the amplitude of the sine wave, that sine wave would fold in on itself. And as you kept increasing the amplitude, you would hit more and more of these folds, resulting in some very complicated spectra. Now, Don referred to this overall effect as timbre generation, and he would refer to changing the amplitude of the sine wave going into the nonlinearity, or perhaps changing a DC offset to that sinusoid as timbre modulation. As I mentioned before, this is used in the Buchla 259, and in the 259, Buchla used a rail-to-rail op-amp. Now, earlier he did use this kind of timbre-generating circuitry in the music Easel, but there he used ECE4450 op-amps, which are a bit annoying. They're quad op-amps, but they don't follow the modern, most common quad op-amp layout that something like a TL074 follows. But anyway, those are distinctly not rail-to-rail op-amps. So the outputs for those are probably maybe a diode drop or maybe something closer to 2 diode drops away from whatever the rail voltage is. So we'll see that the nonlinearity in the 259 seems to be more precisely specified. Let's take a look at one of these. Welcome to Buchla land. Here we have the main input that feeds a bunch of these nonlinearities. One thing that's a little bit confusing is all of these 10K resistors to this 0. That 0 represents ground. And here those resistors are designed to deal with non-ideal op-amp effects. They don't really play an important role in our analysis, so we can ignore them. Just imagine that all of the positive terminals here are hooked to ground. Another thing I'll note is that the ECE4450s required an external compensation capacitor. That's what these 47 picofarad are. Now, most op-amps you're used to using nowadays probably have internal compensation capacitors. The advantage of having an internal compensation capacitor is that you don't have to worry about it. The disadvantage is you're sort of stuck with whatever properties the op-amp designers wanted it to have. By allowing you to choose your own compensation capacitor, you could tailor that a little bit if you wanted to. But you really only want to do that if you really have a good reason to do so and you know what you're doing. An important thing to note is that Buchla ran the 200 series synths mostly off of plus minus 15 volt supplies, but he makes a big deal here to note that the op-amps are being run off of plus and minus 6 volt supplies. That's being generated elsewhere in the circuit. There's a little spot where he uses an op-amp to generate plus or minus 6 volts. Normally, I wouldn't recommend just using an op-amp to develop a supply for another op-amp, but these op-amps aren't being tasked with doing too much, and it would be okay here. Generally, if you're creating a supply for a part that needs it, you would at least want to assist the op-amp generating the needed supply voltages with a beefy transistor to handle the current, or just go ahead and spend the money and get a real voltage regulator. So with all of that out of the way, let's think about what these things are doing. Each of these op-amps is providing a deadband circuit defined by an input resistance, a feedback resistance, and also what I call the load resistance here. Now that load resistance is really the input resistor for an inverting mixing op-amp. So what we see is we have an op-amp down here that's operating as an inverting mixer. Remember, we can ignore this 10K resistor. It's just dealing with some non-ideal effects. You can imagine that the positive terminal here is grounded. So we have a feedback resistor here, and then the input resistors that are feeding it are this 33K and this 68K here. We have this circuit and this circuit, but also the original. So we have the original signal coming in here, going through this 240K resistor in like this. So all of those things are being added up and inverted. But I have another inverting amplifier here. So what is this one taking? Well, it's taking the output of this op amp, that mixing stage, and it's mixing that with the output of this circuit, and this circuit. So those are all getting mixed here. So the original input and these two stages are being mixed in with a plus sign because it's been inverted twice. And these three stages are being mixed in with a minus sign since they're getting inverted once. We also have some interesting circuitry up here, and these are basically designed to operate as voltage clamps at extreme voltages. And in this example output that Don kindly drew here, you can see the effect of the sinusoid being folded back in on itself. I probably should also let you know that Buchla hardwired the 259, and for that matter the music easel, to take its input from the output of a triangle to sinusoid wave shaper. All right, so how does this sine wave get into here, and how do we get interesting variations from it? Well, we have a couple of JFETs here, and these are roughly being used as approximate voltage-controlled resistances. So we have a voltage that's generated up here that's fed to the base of Q10, and that's described as a timbre control. So basically, this op amp here is being used as a primitive voltage-controlled amplifier. So thinking about it that way, ignoring the capacitor for a second, you could think of this 33K resistor as being a feedback resistance, and you can think about this 15K resistor as being the resistance to ground in a non-inverting amplifier stage. So the gain would be something like 1 plus whatever the feedback would be, so that would be 33K, divided by that resistance to ground, which would be 15K. And there's a dozen other things going on in here that I'm ignoring. I'm just trying to get a rough feel for what's going on. But notice that this resistance is in parallel with this JFET. Roughly speaking, as we change the voltage being applied to the base here, we're effectively changing a resistor-like thing that's in parallel with this 15K resistance. And that's how we're able to vary the gain of this circuit here. Now, what I've described here is really quite rough, both in my description and in thinking about a JFET as a voltage-controlled resistance. There's a little bit of the sine wave, the signal that we're trying to control, being added in here, and I believe that's part of trying to make this work a little more cleanly and deal with some non-ideal effects and using the JFET in this way. Now, another game that the 259 can play is that it will also put a DC shift, basically taking this triangle wave and moving it up or down the way it's drawn here to hit different sections of that nonlinearity, basically moving it around horizontally. Buchla called that a symmetry control. It's on the 259, but it's not on the music easel. That symmetry control voltage comes in this direction. It's coming on from off screen here. Now, notice it's coming in through here. Again, part of the sinusoid is being applied to the base, I think to try to smooth out some of the weirdnesses of using a JFET in this mode. Notice it's also sort of being amplitude controlled by the timbre control itself. So the timbre control is affecting both the overall gain that we're getting from this amplifier, and the timbre control is also influencing how much of the symmetry is actually giving this little DC offset one way or another. Now, if you build this circuit yourself, you're not limited to putting in a sine wave. You could put in other kinds of waves and see what comes out and do interesting things this way. But in general, as you increase the gain provided by this op amp, you're getting wilder and wilder effects because you're hitting more and more of those teeth in that nonlinearity. One more thing that I forgot to mention, part of the way this is set up is it looks like Don is also taking part of that sinusoid and is just running it through here directly into this summing node. What's interesting is that he also has some of the sine wave going through into the summing node, but that's going through this weird, complicated pseudo VCA mechanism. Here he has a bit of the sine wave coming in that's kind of independent of whatever all of this stuff is doing. So that's kind of interesting. I can't remember. I don't think I included that in the nonlinearity graph that I made or in the demo I'm about to show you. So what does this actually sound like? What I'm going to do is I'm going to take a sine wave of low amplitude and I'm going to increase the amplitude gradually and then decrease it back to 0. And I'm running that into the nonlinearity of the 259, or at least my rough recreation of it based on my diodeless deadband formulas and whatever values Don wrote in his circuit. One thing real quick, notice he was very particular to designate that these should be 1% resistors. So he deemed these values to be sensitive. There's other places where he did not bother with 1% resistors, indicating that those are less sensitive. And that was important because especially back in the day, back in the 70s when these were being built, 1% tolerance resistors were a good deal more expensive than 5% tolerance resistors, although nowadays the difference in price is between negligible and non-existent. Now, while I'm playing this for you, I'm also showing you a couple ways of visualizing the output. To create these graphs, I cheated a bit. I basically took one cycle of a sampled sinusoid, ran that through the nonlinearity, and then took its FFT. And then I changed the amplitude of the sinusoid going in and plotted it going this direction as I increased the amplitude of the sinusoid, similarly down here. And what I'm plotting using image intensity is the magnitude of those fast Fourier transform bins as I change the amplitude of the time domain waveform going in. So the first, third, fifth, and seventh harmonics that are indicated by those fast Fourier transform bins, I'm also presenting those on the left-hand side here on this plot. And you'll see that these harmonics fade in and out. It's not like you start cranking the volume and one of them goes up and stays going up. As one of them is fading in, another one's fading out. And you get these sonically complicated swirly patterns that are actually reminiscent of what you get from FM synthesis. If you take a sinusoid and you modulate its frequency according to another audio rate sinusoid, you get these amplitudes determined by Bessel functions, which do oscillate. And if you look at graphs of those Bessel functions, they qualitatively look a lot like this kind of thing. Although, to be clear, these are not Bessel functions. They just have a similar flavor. The other thing I should mention is that although in the sound file I increase the amplitude and decrease it again, here I'm only showing you what happens when you increase the amplitude. In the second part of the waveform that you listen to, imagine that you're looking at it going this direction. I'm only showing half of what's equivalent to the total sound file. So watch your speakers because this can sound annoying. So now that you've turned on your speakers, I'll play that for you one more time. And listen closely and you'll hear the various harmonics fading in and out. So that was fun. Now, I mentioned this symmetry operation. In the next slide, what I'm going to do is I'm going to keep the amplitude of the wave going fixed, but now I'm going to add a DC offset to the sinusoid before it goes into the nonlinearity. Here, I'm only plotting the first, third, fifth, and seventh harmonic again because I wanted to compare and contrast with what I had on the previous slide. But now that we've moved things off of being centered around 0, we now do have a second harmonic and a fourth harmonic and a sixth harmonic. Now, you can play games, of course, by changing both of these parameters at the same time, but I thought it would be easiest to develop some initial intuition by just changing one of the parameters and leaving the other fixed. So here's what that sounds like. Notice that's a much more subtle effect in terms of how it changes over time. Of course, you'll get something more drastic if you also change the sinusoid amplitude. I'll play that one more time. It's kind of reminiscent of what you get from doing slow pulse width modulations of a rectangle, but not really. This really is its own thing. All right, I won't be making those noises again anytime soon. So here's another example of this kind of circuit from the music easel. The main sound generating part of the music easel was known as the 218. This particular schematic is showing both the timbre generating circuitry and also it's showing the VCO core itself, the principal oscillator triangle core. I thought it would be interesting to real quickly look at the triangle core here and contrast it with the 259. Remember, the 259 is a later design. So the music easel, I kind of think of it as a missing link between the Buchla 258 oscillator and the 259. It looks very much like the 259 circuit. One main difference is you'll notice that there's a JFET here that's not present in the 259. But in the 259, Don got to use a TLO82 in this particular spot. Here he's using a 741. And a 741 is kind of a terrible op amp. It does not have a very high input impedance. And that is a problem for something like an integrator, since you wouldn't want charge on your integrator cap to leak into this input when you don't want it. So what Q4 is doing is it's basically acting as a voltage buffer. This minus 15 supply and the 33K and this plus 15, this is all rigged up for this to act as a voltage buffer. So the voltage here is being nicely buffered by this high impedance presented at the gate before it hits the negative input here of the 741. The 741 has BJT inputs. The TLO72 and TLO82 have JFET inputs. So basically, they essentially have a JFET like this built into them. So that's the reason you won't see this on a 259 schematic. So looking at the timbre generating circuitry on the easel, we see a couple of back-to-back diodes here that are going to create a distinct voltage clamp that basically is going to level off if you go far enough that you've gone through all of the teeth. In some Buchla schematics, he likes to make a distinction between quiet grounds and noisy grounds. So here he's using a Q to indicate quiet ground, and unsurprisingly, he'll use an N to indicate noisy ground. And again, any resistances you see in positions like this are dealing with non-ideal effects, and you can just think about these kinds of things as being grounded when you do the analysis. The rest of this configuration looks pretty similar. But remember, these are not specialized rail-to-rail op amps being run off of specifically generated voltage supplies. These are just bog standard op amps that he's running off the same voltage supplies that he's running the whole rest of the circuit, which is plus minus 15. And so the output is actually limited between maybe 1 to 2 diode drops of those power supply rails. And something I thought interesting was the fact that some of these resistances here aren't just single resistors. They're actually parallel combinations. Now, sometimes people will do this in order to try to get a resistance that on average will be within a certain tolerance, or I don't know, there may be other reasons you would want to do this. I bet you that this was designed less systematically than one might think. Again, that's a conjecture. I bet he built this circuit on the breadboard and got something within the ballpark and then just started sticking some other resistors in till he got the kind of effect on the scope and in his ears that he was looking for. I don't really know. Again, I don't have a good picture about what the design procedure would be to explicitly construct a specific nonlinearity using all of this kind of craziness here. So there you go. The input circuitry for this is different than the 259. It's actually simpler than what you would find in the 259. The easel doesn't have the symmetry control, so you'll just see this JFET resistor combination where, again, we could figure out that if we didn't have the JFET here, we would have a gain of 1 plus 33K over 6.8K. But we do have this JFET here that's acting sort of as a voltage-controlled resistor. The control signal for it is coming in elsewhere and winds up here. And if I remember right, this is a trim pot. It's not a front panel control. The front panel controls are shown in another part of the schematic. A little bit of the sine wave is actually being added into the base here. And if you look up app notes about using JFETs as rough voltage-controlled resistors, you'll see that this is a thing you can do to try to linearize some of the nonlinearities inherent in trying to use a JFET in this mode. I don't personally mention this very often, but somewhere around 2008 to 2010, I recorded some of the live lectures I did for an earlier version of this class called Electronics for Music Synthesis and posted those online. I posted them to a website called blip.tv because at the time YouTube limited videos to 10 minutes or 20 minutes or something like that, possibly unless you paid more money than zero, which was the amount of money I wanted to pay YouTube. Anyway, Blip TV eventually changed business models and all of those videos were taken down. And unfortunately, I'm pretty sure the drive that I had the videos on was subject to a crash at some point because I couldn't find them. And also, fortunately, these videos had fans, and some people had downloaded and archived these videos, and I encourage folks to re-upload the videos. So they are out there. I tend not to point people to them very often because I'm actually slightly embarrassed by them, because I basically took the cheapest camcorder I could find at Target at the time and stuck it on top of an overhead projector and just left it there. So the quality isn't great, but I'm very pleased that a lot of people watched these and found value in them and found them inspiring. And one day, I came across this really interesting paper called Virtual Analog Buchla 259 Wavefolder that appeared in the proceedings of the DAFX conference, DAFX, Digital Audio Effects. And this is a great conference, and you should read all of the papers coming out of it. This is actually probably the best place to get a detailed circuit analysis of a lot of fancy analog synthesizer circuitry, because the people writing the papers are trying to create DSP models of that circuitry. So the first thing they do is try to figure out the circuitry. And here I was very interested to see them tackling the 259. And if we scroll down a bit, we can see the basic deadband nonlinearity. We can see the way that they're combined to create the weird zigzaggy. And I thought, that's really cool. Let me see what analysis they did, because I wanted to confirm that whatever they did matched mine. And then I was very tickled and excited to find this phrase here. The following treatment of the circuit adheres for the most part to the analysis presented by Professor Aaron Lanterman as part of his lecture series, Electronics for Music Synthesis. So my work in figuring this out and teaching those lectures and in uploading those lectures helped lead to some actual scientific research, and that got presented at a conference. And this makes me incredibly happy. Let's see. So they're presenting the various nonlinearities, and they show what happens when you add them up. Here's the final nonlinearity. Here's what you get when you put a sine wave through it, and you can see the various folds taking place in the output. And then they go through a lot of detail on how to implement this digitally, particularly dealing with the aliasing effect that you get when you take signals and run them through nonlinearities. You're going to get some high-frequency components, and if you're not careful, those are going to get aliased in nasty ways. So a lot of the work that people do nowadays in quote-unquote virtual analog synthesis is how to generate these analog-y kind of effects, but do it in a way that doesn't run into aliasing problems.